Okay, so this is the second set of slides for today's lesson, understanding probability. So we're going to explain the role of probability in statistics and describe and create basic probability distributions. All right, so the purpose of probability models is to analyze samples to make predictions about various types of populations. For example, meteorologists use various models to predict our weather forecasts. Probability is a prediction of what we expect to happen, not a guarantee of what will happen. Oftentimes, meteorologists look at multiple forecast models and select the ones that the one that has the highest probability of occurring, but sometimes a few models have a similar probability of occurrence. So how do meteorologists make their decision? They rely on statistical significance. So that's the key idea here that we're going to discuss. Suppose you want to test whether a die is fair. Every outcome of a fair die is equally likely, with each possible outcome having a probability of 1 out of 6. If you toss a die 120 times, and of those times you roll a 2, a total of 16 times, is the die unfair? So I think the expectation here is that if you roll a die 120 times, so sometimes you're gonna get a 1, right? You may get a 1, you may get a you may roll and it may land on the 3. So I'm listing them uh, just to give us a sense of what might happen. Then you might roll another 1. You may roll a 5, right? Uh, and you'll continue to do this, and assuming you do this 120 times, I think it's fair to to expect that your belief would be that you would not get exactly 1/6 of these landing on uh, in this case rolling a 2. So maybe 2 comes up. 2 is going to come up. Uh, and then you may continue to roll, and then two might come up again. Now, 1/6 of 20, so of 120, 1/6 of 120 is 20 times, right? So along the way, you would expect two to come up a bunch of times, but I think you would agree it would come up close to 20 times, but maybe not exactly 20 times because we're dealing with chance, right? Um, and so the question here is, well, what if it comes up only 16 times? Is something wrong, unfair or wrong with the die? And here we're kind of going with our gut feeling, and I think most of us would agree that 16 isn't um, that different from 20 when you're um, rolling a die 120 times. Now, if you're rolling a die, say 1,000 times, okay, which may be harder to imagine doing that, or at least you know it would take a long time. You would expect roughly, so if it's 1/6 of that, so I'm gonna need my calculator for that. So let me see if I can bring that up. Uh, so 1/6 of 1,000. So 1,000. Oops. We roll it 1,000 times. 1/6 of that I can just divide by 6. So it's 166.6, which is not even a whole number. But that's okay. 166. Uh, so that's about what you expect. 166 or 167. Oops. Let's say 167 just because it's easier to it's a whole number, right? So that's a 6 there. And let's say that if you were that you do roll it 1,000 times and actually only 50 times does the two come up. That is, just subjectively l much less than 167. So in that case, you would say there's something unusual happening. Okay, so that's the idea there. So this is just kind of reiterating that. In another experiment, you toss a die 600 times, you should expect a roll of 2 to come out 100 times. However, let's say that in one experiment, you roll a 2, a total of 100, you roll it to 160 times. So this is the opposite, right? So you're expecting 2 to come out about 100 times. So you wouldn't be too surprised if you roll the dice 600 times and uh, 99, 101, or even a little bit more different. Uh, I think even up to like 85. That would be a little unusual, but not out of the question. Or if you go up to 115, if you roll 115 twos, you might not be that surprised. But if you roll it 160 times, now we're now that seems uh, unusual. So that's very different to the 100 you expect, although it is possible that 160 rolls of two can happen. It's much more likely that the die is weighted. So again, we're just kind of using our subjective. Uh, we'll actually have a value where we'll say, wait, this is way too different. Um, but whenever we think that it's unlikely due to chance, the difference is statistically significant. So this would be statistically significant. Okay, let's look at this example. In an opinion poll, 1,500 people in one state were randomly selected and asked for their opinion of the governor. In the poll, 52% of people selected showed support for the governor. A week later, 54% of a different group surveyed were in support of the governor. Can you conclude that the opinions of the people in the state changed over the course of the week? So what's happening here is you're using this as your foundation. It's like saying, so let's see. So you either show support for the governor or you don't. So it's basically you can think of this as a slightly weighted coin where you show support. Oops. Sorry, I don't know why it does that. Let me try that again. Where you show support, and then so we'll use S for showing support, and then let's use N for not showing support. But it's essentially uh, heads or tails, right? Except that this this is 0.52 instead of 0.50, and so this would be 0.48. Not showing support, so it's not exactly a fair coin. Well, um, so so this is like so those are the basic odds, and then you can think of like flipping this weighted coin 1,500 times, and um, so 54%. Let's see what's 54% of 1,500. 54% of 1,500. Oops. 54% of 1,500. See if I can get a calculator. So, calculator. So we've got 1,500 people or coins, and 54% of that. Oops, let's try that again. 0.54 of 1,500 is 810. So 810. So 810 uh show support, and then the others did not. So the question is, what were we expecting? Well, we were expecting, based on this theoretical probability, we were expecting 52% of the 1,500, which is 780. So we were actually expecting 780 based on this probability to support. Well, those are not vastly different. And so we would conclude it's not statistically significant. So since this is only a 2% difference, it's reasonable that the people's opinion of the governor didn't change at all. That's what's happening there. So it wouldn't be statistically significant. Okay, so mm, let's let's go on to let's look at this one. Let me see if this one's going to be significant. Okay, so Thomas tosses a coin 300 times. Of those 300 times, he observes heads a total of 250 times. Now, so 200. So we might be able to do this without the calculator. So he observed heads 250 times. Wow, that's so 250 out of 300. That's definitely not what you expect from a fair coin. So this is 25 out of 30, which is 5/6 of the 5/6 of the time. And you're actually expecting a 50/50 chance. And so you're expecting that heads comes out um 150 times, and which is 50% of the time. And this is really much higher. Um, and so um, so this would be considered statistically significant. Now there's something a little bit hidden here because it says calculations show that the probability of this occurring by chance is less than 5%. Uh, there's a hidden computation here that we're going to learn about later, but what you have to imagine is all the things that could happen when you toss 300 coins. You could imagine that heads comes up uh, all 300 times. Now, it's a possibility, but it's going to be highly unlikely. You couldn't even imagine tossing a coin and getting heads 299 times and just getting, a one tails somewhere. It may be the first thing you toss, or it may be somewhere in the middle. It's highly unlikely. You could uh, imagine tossing a coin and getting heads 20 times. Still highly unlikely. And so we have to be able to somehow, and we're not there yet, but we're gonna have to somehow imagine all the possible things that happen and then deciding how unlikely they are, whether it's 5% of the time or less. In those cases, that's when we say, oh, wait, something uh, very unusual is happening. Okay. All right. But we'll flesh that out some more later. In order to more formally quantify the statistical significance of an observation in a statistical experiment, we can introduce the idea of a random variable. A random variable X is a variable that is subject to change due to chance and events. Okay. So we might list, let me see. So we might list um we might list we might make a table. Okay. And we'll start with something easy and that we've dealt with already. Uh, let's see the probability of getting heads, and let's on one of the coins, assuming we have two coins, um, we might have 0 heads. We might have the second coin come out heads, so where there's only one head. We might have the first coin come out as heads and the second coin come out as tails. That's also one. Um, or they might both come out heads. So let me make an adjustment here. So here, little error there. So that actually would be the probability of X happening. So the probability of getting no heads is 1 in 4. The probability of getting one head is a 2 in 4. And the probability of getting two heads is a 1 in 4. So that's a probability distribution, and X is a random variable that can take on X equal 1, X equal 2, 0, X equal 1, X equal 2. So this is a probability distribution. The probabilities are between 0 and 1, just like they were over here. A quarter, 2 quarters, 1 quarter. They should add up to 1 if you sum them up, right? If you take a quarter plus 2 quarter plus a quarter, that's equal to 1 whole. Okay, so just simple question, is this probability distribution? Well, and this is not showing where the numbers are coming from. So this is pretty theoretical, but X can take on 0, 1, and 2. And with these probabilities, again, this is not tied to the previous example um, where we rolled 2 coins, where we flipped 2 coins. Uh, but if you add a half and a third and a sixth, they're equal to 1, so it's a probability distribution. Okay. Here's another example. A news program reports that 46% of the population are in favor of a certain issue and 48% are against the issue. Create the corresponding probability distribution table. Okay, so let's Okay, so um, let's just read this. The first thing to know is that the given probabilities 46 and 48 only add up to 94. If yes and no were the only possible responses, these values would fail criterion 2 for the probability distributions. However, it's common practice to report only yes and no percentages on a survey with the understanding that the remaining percentage of the population is undecided. And so this is the way you would do the probability distribution. So it's essentially like a three-sided coin, if you can imagine that. And sometimes it lands on yes, sometimes it lands on no, and then the other time it lands on undecided. And if you will, if we want to continue with that analogy, it's a weighted coin, and this is how it's weighted. You could use dummy variables and make this a 0, a 1, and I suppose a 2 here. Um, okay, if you wanted to put numerical, uh, if you want to turn it into a numerical variable. Okay, determine whether or not the distribution is a probability distribution. So we can see right away that neither of these is between, actually, the second one is okay, but the last one is not between 0 and 1, so it is not a probability distribution. Okay, a student randomly selects classmates from their local community college and asks how and asks each how many siblings he or she has. The table below summarizes the data. Construct a probability distribution. Okay, so all we have to do here is list probabilities. So this would be 8 out of, we have to find out how many total there are. So 8, 17, 11, 3, 1, 8, 17, 11, 3, 1. 8, 17, 11, 3, 1. That's 40. So all of these would simply be, the probability would be 8 out of 40. You can certainly reduce. The probability would be 17 out of 40, and so on. And if you convert these to decimals, you would end up with these values as the probabilities. And they all add up when you add up 0.2, 0.425, 0.275, 0.075, and 0.025. They add up to 1. Okay. And just looking at a couple of examples from the homework. For the probability distribution of x given below, find m. So what you have to do here is you know that that all of these probabilities should add up to 1. So we're going to just set that up and then solve for m. So that's what we're going off of here. is that all of these probabilities should to should add up to 1. Let me try this again. So it's m plus 2m plus 3m plus 4m. So it's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10m. I'm going to do it on this side. If you add up all the m's, you end up with 10m, and they should all be equal to 1. And so if you divide both sides, you learn by, sorry, I'm having trouble with the interface here. But if you divide both sides by 10, you'll see that m is 1/10. If you divide both sides by 10, you get 1/10 for m. And then on the last one, let's see, an ultra die has 1 dot on one face, 2 dots on 3 faces, and 3 dots on 2 faces. The die is to be tossed once. Let x be the number of dots on the upturned face. Construct a table showing the probability distribution. So this was one where you had to fill in the possibilities. So possibilities are 1, 2, and 3. It is a 6-sided die. They don't say that, but I think we can assume that. It's a 6-sided die. One of the faces has 1 dot, and then 3 of the faces have 2 dots. So there's a 1 in 6 chance that it has 1 dot. And then there's 3 out of 6 chances that it has 2 dots. And then 2 of the faces, the remaining 2 faces of the 6-sided die have 3 dots. And so this is how you would fill that in. One more example. And there's quite a bit going on here, but City Council sends out a survey to city residents to determine the support for a new school being built downtown. The survey asks residents whether they support the new school being built and their location in town. Out of those who respond, 376 of the 641 residents surveyed in Ward 1 support the new building being built, while 214 of the 398 residents surveyed in Ward 2 support the new school. Assuming the location of residence has no association with supporting the new school being built, the probability of the results, this is where the key is. The probability of the results of the survey being due to chance is calculated to be 0.12. Okay, so they're giving you a lot of data here, and For this particular example, those values are not helpful. It's really the fact that this outcome can occur by chance 12% of the time, which seems low, but in fact, we always or often use 5% as the actual cutoff point for saying that something is occurring at an unusually low rate compared to what is expected. And we'll really flesh that out later. But because this is not below 5%, we say it's not statistically significant. Okay, I think that's the only one that uses that phrase. So, if for this homework, if they give you results of something occurring due to chance above 5%, then you say it's not statistically significant. If they had given something here that was like 0.04, then you would say it is statistically significant. Okay, I'm gonna go ahead and wrap this one up, and that's the last video for today.